So, yes, 1-3 is 146. So 146. Or 147. Yes, 147. 33. So it's wanting cosine of 4 degrees, 50 minutes. Yes.
Attention Concord High School. Seniors, the Grand Lake Savings Bank Board application is due Friday. It is in your class of 2025 Google Classroom. The Cherokee word of the week is kamama, which means butterfly. Thank you and have a great afternoon.
So there's two ways we can do this. One is that we convert 40 degrees, 50 minutes, 15 seconds just straight into degrees. So we divide the 15 by 60, add it to 50. Take the 50 plus that decimal, divide it by 60 so that we have it as 1. Now the other way is in the graphing calculator. Now the first thing you need to make sure is that your graphing calculator is in degrees, not radians, because if it's in radians, it's going to throw a fit. Well, not throw a fit, it's just going to give you the wrong answer. So mode. As we can see here, radians, we're going to switch it over to degrees. So the one we're looking at is cosine of 4 degrees, 50 minutes, 15 seconds. So we can say 4 second angle degrees, 15 second angle minutes, or was it, I think it was 50.
Yeah, 50 and then 50.
Second catalog. So one way is to convert our degrees, minutes, seconds, is to convert degrees, minutes, seconds back into just degrees and then plug it in. Or to plug it in with degrees, minutes, seconds. Because if we did it, converted it back, 15 seconds is 0.25 minutes. 50.25 divided by 60 is that plus 4. 0. Cosine of 4.8375 is 99.64. So we get the same value. It's just which way do you want to do it? Does that make sense? So you can either convert it from degrees, minutes, seconds to just degrees, or plug it in as degrees, minutes, seconds. Now, if you do have the calculator set in radians, it's going to give us a completely different answer. So the answer should be 0.9964. 0.9964. With sine, cosine, tangent, secant, cosecant, cotangent, we're going 4 places after the decimal.
Can I write that down on my homework?
Yes. I don't think you've... Did you turn that in?
It's on the back side of the... I hadn't finished it yet.
Okay. You're welcome. Any questions, other questions on the homework? Okay.
Question 25.
One.
The quadrants, I still know how to do it as a negative, but if I add the pi or something like that.
1, 1. Question number what?
25.
So with these two here, because 90, 180, 270, and 0, comma 360. Now A, 130, is going to be over here in quadrant 2. Now negative degrees, we go clockwise. Positive degrees, we go counterclockwise. So if we go negative 0.83 degrees, it means we're starting at the positive x-axis and going clockwise 8.3 degrees. Well, going in this direction, 270 is actually negative 90. And going that way. Now the other way, and this ends up being down here in quadrant 4. Now the other way we can look at it is we can take that angle and add 360 to it, because that's one full circle to make it positive. And if we add this here, 7, 9, its complement, or its coterminal angle is 351.7 degrees, which would be going clockwise, which also puts us in quadrant 4. So for some of our negative angles, radians or degrees, we can add 2 pi to it to get it back to between 0 and 360, or 0 and 2 pi, and it's a little bit easier to figure out where it's at. So one way you can do that is, so what's the degree measure?
Negative 132.
So negative 132 degrees, and we have minute seconds. Well, the minute seconds is really just a decimal, not a whole lot bigger. So if we look at negative 132, well, we can add 360 to it to see what it is as a positive angle. 8 should be 228 degrees. Okay, 90, 180. So we're over here in quadrant 3. The minutes and seconds would deviate a little bit, but we're still going to be in quadrant 3 because it's just a decimal point. Because what is the minutes? 50 minutes and how many seconds? Oh, just 50 minutes. Well, that just means we have 50 divided by 60, 0.83 repeated. So we're really saying that it's negative 132.83 repeated. So it's, at most, it's going to make this, instead of 228, 227.16 repeated, which isn't going to take us away from where we're at. We're still in the third quadrant. Does that make sense? So some of these, finding the quadrants, easier just to get it between 0 and 360, 0, 2 pi, and figure out where it lands. Whereas 0 and 2 pi, if you want to convert from degrees to, or from radians to degrees, it might make it easier to work with. Questions on this here? Questions on anything we've done so far? Okay. Okay.
Cosecant in the calculator is with sine,
CSC is 1 over sine, yes. SEC, 1 over cosine, yes. Yes.
but cotangent is just over tangent, right?
Cotangent is 1 over tangent, yes. And they're also the vice versa too, because tangent's 1 over cotangent, and cotangent's 1 over tangent. We flip it. Sine and cosecant. Cosecant's 1 over sine, sine's 1 over cosecant. Cosine's 1 over secant, secant's 1 over cosine. We have that flip. And I believe we did this one on Friday, yes? Okay. All right. So this is what we're working on is 1, 3.
Okay. Oh, then I don't remember that. Thanks.
Was that on that one paper, the separate paper?
Yeah, so it's the one that I gave you a separate paper to add to it.
Did I finish P2?
I do not.
Okay, go look at that. You need to get that. That's really far behind.
Jessica,
Actually, it's not. This.
you've turned in P1.
I've turned in P1.
Yes,
Oh.
that's it.
That's literally it. That's all I did. That's all I did. Are you sure? P1?
Yes. Well,
That's right here. No, you said that's the only one you've turned in.
yes.
Yeah, then why is it right here? Because he graded it and gave it. No, because he helped me on this one. Actually,
That
he helped me on this one. See, I don't think I have to.
flip. I'm not gonna worry about it then. Because I do remember grading P1 for I think everybody, but
I know that me working in the college shop. It's like something that we didn't. So you still. I don't know how to do it. You want me to just not do it?
I think you've already done it. That might be an extra one you work stuff out on.
Probably did.
All right, guys. We're going to look at this here. So we have, y'all found this in the notes. Prove that the trig equation is true. Yeah, it's the extra one. Yep. So what they want us to do is make the right side look like the left, make the left look like the right. We want them to show that these are equal. So for this here, we need to prove that cosine times secant is equal to 1. Now secant, as we've said already, is equal to 1 over cosine, yes? So we can say that cosine of our angle is being multiplied by 1 over cosine. Because it's true that secant is equal to 1 over cosine, so we can replace it. Questions on this so far? Yes. Okay, now we can multiply these together, which will tell us that we have cosine of theta over cosine of theta. And cosine of theta over cosine of theta is indeed 1, so 1 is indeed equal to 1. We've proven that those two are equivalent. Questions on this here? Now, one of the things with proving these statements or doing these proofs with the trigonometric forms, we can't move things across the equal sign. I can't add things to both sides. I can't multiply both sides by something. And the part of the reason for that is here we're wanting to prove that this equation is true. We want to prove that this side is equal to 1. We're wanting to prove that they're equal. And if we start trying to move stuff from one side to the other, we're assuming that they're equal. Because our properties of equality that let us move stuff from either side or multiply both sides by something is a property of equality. We can't use the properties of equalities to prove that it is equal. So really, when we look at these here, we can treat both sides as two separate statements. So for this one here, we want to prove or show that secant of theta plus tangent of theta times secant of theta minus tangent of theta is indeed equal to 1. So the first thing we're going to do to prove this is multiply through by secant. our secant times secant is going to be secant squared of theta. It's being multiplied by itself. Secant times negative tangent is negative secant of theta, tangent of theta. Tangent of theta times secant of theta is going to be plus secant of theta, tangent of theta. And lastly, tangent of theta times negative tangent of theta is negative tangent squared of theta. We could write the equals 1. We don't have to because, again, we're trying to show that this is 1. That's the whole goal. Questions on this so far? Now, at this point, we do have like terms. Negative secant tangent and positive secant tangent. What does that give us? 0. They cancel each other out. So those two are gone. And what we're left with is secant squared of theta minus tangent squared of theta. Now, at this point here, we need to get this equal to 1. Now, in your note sheets, the full note sheets, let's look at the Pythagorean identities. Is there one of those that has secant squared or tangent squared? I think there is. Tangent squared of theta plus 1 is equal to secant squared. So it's in 1-3. So look on the other side. It should be one of the last slides. Yep, it's kind of small. I will print off a bigger one, but I think it says tangent squared plus 1 equals secant. We have this here, yes? So that means this secant here is the equivalent of tangent squared of theta plus 1. Questions on how we were able to replace that? Does that make sense how we replace that? What is secant squared of theta? You're good. No, because if it doesn't make sense, it's not going to make sense until we see it. Because secant squared of theta, by definition, is tangent squared plus 1. That's just by definition. So we can replace secant squared with tangent squared plus 1, because those are equal. Does that make sense how we got from there to there? Yes? Well, tangent squared minus tangent squared is? What are we left with? So we did prove that the original statement, that secant plus tangent times secant minus tangent is indeed. Questions on this here? Do we kind of get how this works? And again, one of the students I had previously said this felt like cheating in a little bit because we're just taking these formulas and using them how we want to make them say what we want. Yes? And these trigonometric identities, cotangent squared plus 1 is equal to cosecant squared and sine squared of theta plus cosine squared of theta is equal to 1. We will be using these a good bit, especially when solving trig. And we will manipulate them to get what we want out of them. Because here, I'm going to erase this. Erase that. Now the top one, tangent squared of theta plus 1 is equal to secant squared. I could also say tangent squared of theta is equal to secant squared of theta minus 1. I just subtract 1 from both sides, yes? Over here. Secant squared of theta minus I can replace tangent with tangent squared of theta minus 1. Or sorry, not tangent. It'd be secant squared of theta. Because tangent squared of theta is equal to secant squared minus 1. Because all we did was take tangent squared plus 1, subtract 1 from both sides, and I can replace tangent. Now let's see what happens. If I distribute the negative, we have secant squared of theta minus secant squared of theta. Our negative 1 makes it plus 1. Secant minus secant is 0, leaving us with. There's more than one way to prove these. It's just figuring out how we want to prove them to get there. Does that make sense? Well, if that's the case, does that mean we could have proven this one differently? Well, yeah. Because cosine is equal to 1 over secant. Which would be secant of theta over secant of theta, which is still 1. It's picking a root and going with it with these proving these statements. Questions on this here? All right. Many different applications for solving right triangles. In this type of application, you're really just given one right triangle, acute angles, and you're trying to find the sides. Because we can talk about elevation, angles of depression to do this here. Because we have this as one of the examples, and it's just really setting the right triangle up and going from there. Does that kind of make sense? I mean, we can do this in any way, shape, form. I mean, we could talk about lights on a light pole or football field. Because I think y'all remember when they, not the new ones, the LEDs, but the ones before they got those new lights put in. Incidentally, they actually contacted me about trying to figure out how to get them set up. And it's possible. Because all we do is talk about this here, and if we know where on the field you want the center of that light to be, all you're talking about is a right triangle to get there. Yeah. And I didn't even have to aim them. Because we can think of it in terms of, up here's the light, going straight down to the field and out. If we're talking about just out, they want it to go so many yards out. Height of the pole, distance, we can find the angle because tangent of this angle is opposite over adjacent. So we can know how far out if we're going straight out. But what's interesting, let's see here. So if we think of this straight out, if we said it was off to the side, we can lay another triangle flat and actually do over. You can actually do more than one of these. So, but that's it. That should be. But that first half, 6 through 10 even, (15 through 19 odd) was the AMI work. So you're not, 1-3 is not going to include that. That's just the AMI. You've already got that done. So the only other part of 1-3 you're needing to do is 25 through 35, 37, 40, 43, 49 odd.